we're going to do an example here where we're going to use rectangles to approximate the areas. And in this example, I'm going to give you the function. So we're going to use what we know right now. We're going to use RAM, and actually we're going to use RAM more than any of the other ones, not because it's more accurate, but because when we start adding more and more rectangles, it's going to be the easiest one to work with. And since as we approach infinity, they all end up essentially being the same thing, we're going to choose the one that's easiest to work with. So we're going to use RAM. What do you think this subscript 4 means? 4 rectangles. So this means that n is 4, we're going to use 4 rectangles. So we're going to use RM4 to approximate the value of this integral. And then I put the little asterisk here. When we're done, we're going to see how close our approximation is. The first thing I would do here is draw a picture. Let's try to get an idea of what this is going to look like. So we're dealing with x values between 0 and 2. There's no need to add more to our picture than necessary. So I'm just going to use the first quadrant here since everything's going to be in the first quadrant. And we're going to go from 0 to 2 on the x-axis, which means with the x squared function we're going to go from 0 to 4 on the y-axis. And so our function, we try to make it look somewhat accurate, which could be helpful here to some extent. We'll have those points on it, and so it'll look something like that. So there's your x squared function. Now we're going to use 4 rectangles, which means we're going to divide this into 4 subintervals. First thing I want to do is figure out what the width of each one of those is going to be. So I'm going to write down here, delta x equals. What's that formula going to give us? So yeah, it's going to be b minus a, so 2 minus 0. B and a are just the lower limit and the upper limit of our integral. So we do 2 minus 0, that's the width of the interval, and then divide by the number of rectangles, which is 4, and so the width of each interval is going to be 1/2. So I'm going to go over on my x-axis and mark off every half for the right edges of my rectangles. Now, since we're using RAM, I'm going to go to the right edge of each of those subintervals, and I'm going to start drawing my rectangles. You can go ahead and do the same thing. So I'm going to go up to the function, and then over to the left from there, and get each rectangle. Now, it's not necessary to have a perfectly accurate picture. You want a picture that's going to give you an idea of what's going on, and maybe enough space in your picture that you could do a little bit of the work there, so that you kind of have an intuitive idea of what each of the numbers means. So I think that's going to do the job for us. So what we're trying to do is find the area of those 4 rectangles added together. First thing, keep in mind we never want to start writing stuff out without saying what it means. So for this particular problem, I could do one of 2 things. I could say the value of the integral from 0 to 2 of x squared with respect to x is approximately equal to. We're doing an approximation for this integral, so I could start with that. Or the other thing I could do is I could say RAM 4 is equal to. So even though this is an approximation, we're finding the value of this approximation exactly, so we could use the equal sign. So we could show that we're approximating the integral, or we're finding the value exactly of this this right rectangular, using this right rectangular method. Either one of these would be acceptable for me. I'm going to go ahead, I'm going to use the first one, mostly just because I need space and need to clear the other one out. And this integral is going to be approximated by the areas of these rectangles. So for each one of these rectangles, I'm going to take what times what? 1/2, which is delta x times the height, right? So since I'm going to take 1/2 times each of the heights, I'm going to factor that 1/2 out from the very beginning. So I'm going to have 1/2 times, and actually, let me back up a step here. I'm going to write this in using variables first. so that we end up with something, some sort of formula almost. So we're going to take the width of the interval. You don't need to do this, but I want to write this down so you can see what we're doing. And then I'm going to multiply that by f of, well, each of the right endpoints. I'm going to leave these open for a second. So what we need to do is figure out what we're going to put into each one of these. So since we're using the right endpoint, a common notation, this is the notation I'm going to use, for each one of these x values is the left endpoint we would call x sub 0. The right endpoint of that first subinterval we'll call x sub 1. The right endpoint of the second interval we'll call x sub 2. The right endpoint of the third subinterval x sub 3. And the right endpoint of the fourth we'll call x sub 4. Now, obviously, we're going to have to figure out what each one of those is, but I could use those. I could just put those into this right here to kind of get a formula of sorts. Since we're using the right endpoints, we're going to have x1, x2, x3, and x4. Now, I'm getting a little ahead of myself here, but I'm kind of building up to a formula because eventually we're gonna want this number of rectangles to be variable. We're gonna want to be able to use 10 rectangles or 100 rectangles or 1,000,000 rectangles or infinitely many rectangles. So one thing we can do here is take this part right here and rewrite it, well, kind of simply. Anybody know how we could do that? Using something? We can use sigma here to simplify that expression. So we could take the sum of f of x sub I as I goes from where to where? 1 to 4. Now, I am overcomplicating this problem right now, right? You guys are thinking I could have this done and have 7 other problems like this done by now. But what we have right here is a formula that not only works for 4 subintervals, but I could say I equals 1 to n and make n any number I want. The only trick then is figuring out what x sub I is for each one of those. All right, so now that I've overcomplicated it, let's simplify it again. Let's get rid of the sigma notation. Let's go back to what we have right here, and let's just figure it out for this particular problem. We'll talk about methods we can figure out in general later. So this is going to equal delta x is 1/2. I'm going to keep the f in here for now. So it's going to be f of what? What's the first one going to be? 1/2. So how did we get the 1/2? Let's think about this a second. I started at 0 and added on delta x, right? So I start at the left endpoint and add on delta x. So it's going to be f of 1/2. Then the next one is going to be f of so this is going to be f of 1. And how do we get the 1? We started at the left endpoint, added delta x to get to the first one, and then we add delta x to get to the second one. So another way to think about this is we start at the left endpoint and add delta x twice, right? So for the second term, we added delta x twice. What's the third one going to be? 1.5, 3 halves, 1.5. I like improper fractions, personally, over mixed numbers. Mixed numbers are kind of hard to work with. So I'll always use mixed numbers over, I'll always use improper fraction over mixed numbers. And then another way to think about getting this, we take the last x value and add 1/2 or add delta x, or we could start at the left endpoint of the entire interval and add delta x 3 times, right? So for the third one, we added delta x 3 times. Plus f of 2. You guys are probably getting sick of me saying this, but how do we get the 2? Adding delta x again. So we start at the left endpoint and add delta x 4 times. Okay? I think you're kind of seeing the beginnings of a formula there, right? Okay, cool. We'll get to that later, though. All right, so each one of these we can evaluate. We got 1/2 times. What's f of 1/2 going to be? Well, what's f of x? X squared. I'm doing more work than you probably like here, but I'm gonna just put the 1/2 into the function. It's okay if you were to skip this, but I want to make sure that you understand what's going on. So I'm going to take each of these x values now and plug it into the x squared and get this. And then now it's just a matter of simplifying that. So we're going to have 1/2 times the quantity 1/4 plus 1 plus 9/4 plus 4, which is what, 5 plus 10/4, so it's going to be 7.5 or 15/2. And then times the 1/2 out front, it'll be 15/4. As far as units go, the units are almost always going to be different along the x-axis and the y-axis. So I'm not really concerned about units right now. When we start dealing with applications problems where we might have like time along the x-axis and we might have like a speed along the y-axis or some sort of rate, it's almost always going to be some sort of rate when we're finding areas. Then we can worry about units. And actually, in those cases, it's not usually going to be units squared because they're not going to be the same. So a lot of times there's going to be canceling of units, and we'll deal with what those units mean when we get there. So don't worry about units for now. We want to use our calculator to check the accuracy. So let's actually use our calculator to evaluate this integral. So we get that the integral is approximately equal to 15/4, which is 3.75. Let's see what the calculator says as far as the actual answer. So we're going to, I'm going to write this down here. The integral from 0 to 2 of x squared with respect to x is 2.667. Quick question about, or not question, quick comment about accuracy. You have the option to either round, like I did here. It's 2.667 if you round that thousandths place, or you can truncate. Truncate just means cut off. So your calculator gives you this, right? And then it may round the last digit, it may not. What you can do is just cut this stuff off here and give that. You don't have to round that last digit. All right. The College Board, which is the group that gives AP tests, accepts that, so I accept it also. All right. Now, this is not a very accurate approximation, is it? Now, let me ask this. Is the approximation about what we expected it to be as far as an over or under approximation? Would we expect this to be bigger or smaller than the actual answer? Bigger. And you can see that from the picture, right? I should, at some point, I should be able to say, okay, we have an increasing function, and we're going to use right rectangles, and you should be able to tell me, okay, that's going to give us an over approximation. Right now, it's okay to just look at the picture and say, okay, these rectangles are bigger than the actual area we want, so this should be an over approximation. So the fact that we got a number that's bigger than what the calculator gives us, that tells us that we probably did something right. Unless we got an answer like 1,000,000. That's not very close. This answer isn't very close, but you can also see there's a lot of area outside of our region here that's inside of our rectangles. So you can see that our answer really shouldn't be that close. It's going to be off by quite a bit.